Unit 3, Lesson 3 is all about the relationship between a graph, the first derivative, and the second derivative of that graph. And so after you use the mean value theorem, after you have that, you can prove intervals where a graph is increasing, where a graph is decreasing. And that leads to what's called the first derivative test, finding local minimums and maximums of a function. Coincidentally, a lot of times those are global maximums and minimums, but in calculus AB, if it's a global maximum or minimum, you're given a continuous function on a closed interval. Anyways, so hopefully by the end of this, you'll be able to find and justify where local extreme values occur using the first derivative test. So, well, if you're sitting in my class, we're doing this a second time. It's like a review from the day before because, explaining where a function is increasing, explaining where a function is decreasing can lead to, or at least should explain, where that function has a maximum or a minimum. And so what I'm hoping you'll see is kind of the same process. So if we want to know where g of x is increasing and where g of x is decreasing, we should consider the same thing first always, and that's, of course, continuity. So g is a polynomial, so g is continuous and differentiable everywhere. So we'll write that down to begin. And then, intervals where a function is increasing or decreasing has to do with the first derivative. So this should all be pretty review-like. We're going to find g prime of x, 6x squared plus 6x. We're going to look for critical values. We let g prime equals 0, and we get x equals 0 and x equals -1. Since g is differentiable everywhere, g prime is always defined, and we're not going to find that kind of critical value. Okay, so from there, we can make a sign chart, and hopefully you know how to make a sign chart. So the sign of g prime, well, we can see g prime is positive from -infinity to -1 and from 0 to infinity. So g is going to increase on those intervals. And so that's where I write. G is continuous. G prime is greater than 0 on the open interval, -infinity to -1, and on 0 to infinity. So g of x increases on -infinity to -1 and on 0 to infinity. And remember, we're going to include those endpoints, -1 and 0. G prime of x is less than 0 from -1 to 0. So g decreases on the closed interval, -1 to 0. Okay. And so if you look at the sign chart underneath, I've drawn these little, I don't know what I hit there. Oh, I hit a zoom in. I've drawn these little line segments kind of indicating from -infinity to -1, g increases, then g decreases, and then g increases. And of course, we can use this same information to find and justify where that same function has local extreme values. So I cut and pasted the beginning because g might have a maximum or minimum at those critical values, the same places where g might change from increasing to decreasing or decreasing to increasing. So it's all kind of how we write everything out. Maybe I can get white in here. I really don't like yellow. Okay. And so hopefully, that sign chart makes a ton of sense to you, and it's pretty obvious that g has a local maximum at -1. So I'll start off with g of x is continuous. And then I'm going to say at x equals -1, g prime of x changes from positive to negative. So g of x has a local maximum at x equals -1. At x equals 0, g prime changes from negative to positive. So g of x has a local minimum there. Ooh, a lot of writing. Okay. And so what we're relying on here is, well, I think it's, if you understand the words, pretty logical. What must be true about the first derivative of a function before and after some interior point, as in not an endpoint, in order for that function to have a local maximum at that point? So, here's some function. In order for that function to have a maximum, well, to the left of that maximum, that function has to increase. To the right of that function, to the right of that maximum, the function has to decrease. And so another way to say that is that the sign of that first derivative has to change from positive to negative, so long as that function is continuous at the point. Right? Because if you had a graph like 1 over x squared, right? 1 over x squared changes from increasing to decreasing at x equals 0, but we can't find a maximum. That graph isn't continuous. There's no highest y value. Okay, so let's think about this then. Same kind of question. What has to be true about the first derivative of a function before and after an interior point in the domain for that function to have a local minimum at that point? So we know what a local minimum is, and what happens over here? F decreases. So that means f prime is negative. And to the right of that minimum, f increases, which means that first derivative is positive after the minimum. And of course, that function has to be continuous at that same x value where the first derivative changes signs. So, this thing called the first derivative test, you first need to determine continuity. And, a lot of times you'll have polynomials or e to the x or something you just know is continuous. And the graph doesn't have to be continuous everywhere. Just know if it has a discontinuity, you better not say that that graph has a maximum or minimum at the discontinuity. We're going to find the first derivative so that we can find critical values. And then we're going to make a sign chart to test intervals and just really look for where that first derivative changes sign. And then, so I think it was 2013 or something. I forget because that's such a long time ago. It used to be that just making a sign chart is enough, but you can actually look it up. There's a white paper on College Board, and it's basically sign charts are not enough. Your job is to explain what you see in the sign chart. So you have to say, hey, f prime changes signs, all that stuff. We'll practice in a moment. Now watch out. Depending on context, you have to correctly choose between this first derivative test, this looking for a maximum or minimum in a sign chart, and the extreme value theorem, the candidates test. It's just one of those we're playing the game sort of things. So we're going to use the first derivative test to find where the local extreme values occur for x cubed minus 12x minus 5. Now, you should kind of know already, x cubed minus 12x minus 5 has a general shape like this. So it's not going to have an absolute maximum or minimum. The best we can do is a local maximum, a local minimum, and I'm kind of expecting to find a local maximum to the left of a local minimum. But our job is to find and prove all of that. Okay. So we're probably on board with this by now. We're going to be looking for continuity, and x cubed minus 12x minus 5 is a polynomial, so it is continuous and differentiable everywhere. Well, then what? Well, maximums and minimums might occur at critical values, so we need to find where that first derivative is equal to 0 or undefined. The derivative of x cubed is 3x squared. The derivative of negative 12x is negative 12, and the derivative of 5 is 0. So we're going to set y prime equal to 0. We don't have to worry about y prime being undefined because y is differentiable. X cubed minus 12x minus 5 is differentiable everywhere. And so 0 equals 3x squared minus 12. And maybe I should have written more out, but that's 3 times the quantity of x squared minus 4. X is equal to positive or negative 2. Okay, so we need to make a sign chart. How do we, well, maybe I should walk through that a little bit more slowly, and this will pop up on the next page. So on your sign chart, that's just a number line, and we're going to label it. Sometimes you have a sign chart for y prime, sometimes y double prime, f prime, all sorts of things. We're going to put a little x down here by this right arrow saying the inputs are x, and we're going to put all critical values on that sign chart. Then we have to test intervals. Critical values are useful because that's the only place a function, the derivative could change signs. When that derivative is equal to 0, that derivative might cross over the x-axis. And if that derivative is undefined, jump discontinuity, maybe that graph goes from being above the x-axis to below at that discontinuity. Okay, anyways. Now this is the sign of y prime, and ideally we'd do this in your head, but maybe that's hard to follow along. So we're going to choose some number in between -2 and 2, like 0. And I'm doing this in my head, but I guess I'll write it down. And we're going to put 0 into y prime, and we don't really care what the number is, we just care about the sign. So, when I do 3 times 0 squared minus 12, I get negative. So if y prime is negative from -2 to 2, well, that means x cubed minus 12x minus 5 decreases on that interval. So I draw that little decreasing bit underneath. And then choose some number greater than 2. And most people say like 3, but I think it's easier to use a number like 10, because 3 times 10 squared overpowers that 12, and we know for inputs greater than 2, y prime is positive, and x cubed minus 12x minus 5 increases. Then we need something less than -2. How about -1,000,000? And -1,000,000 squared times 3 is going to be very positive and greater than the -12. So we get that y prime is positive from -infinity to -2. That's how you make a sign chart. Okay, so here's a 2-color sign chart. So exciting. All right, so now our job is to explain what we see in the sign chart. Now, we already said that x cubed minus 12x minus 5 is continuous, but we don't want to forget that, so I always write it twice. And then what do we see? Well, remember, we're not looking for increasing and decreasing. Even though we have that information, we're looking for maximums and minimums. So what do we see? At -2, y prime goes from positive to negative. That's our evidence. And then a conclusion. So at x cubed minus 12x minus 5 has a local maximum at x equals -2. And if you do this like increasing and decreasing bit, it's pretty obvious. Oh yeah, local maximum. And again, that matches up with the graph we expected from the beginning, or at least that, it's not really a parent function, but we know what to expect. Anyway, so what's our other evidence? Well, our other evidence is going on at x equals +2. What happens at +2? At x equals 2, y prime changes from negative to positive. That's our evidence. What conclusion can we draw? So x cubed minus 12x minus 5 has a local minimum at x equals 2. To me, that's pretty straightforward, but I do this every year. And so here is a graph from Desmos that completely confirms what we just wrote down. This graph definitely has a maximum at -2 and a local minimum at +2. So we're going to do that again. We're going to use the first derivative test to find where local extreme values, maximums or minimums, occur for -x to the 4th. Now, -x to the 4th, definitely not a parabola, but a U-shaped curve, and it should just have a local maximum if we do the math correctly at x equals 0. So that's what we expect. Okay. So -x to the 4th is a polynomial, so it's continuous and differentiable everywhere. Continuity is an easy one. That maximum is going to occur at a critical value, so we need to find y prime. And of course, y prime is -4x cubed We'll set y prime equal to 0 and end up with the one critical value x equals 0. So now we need to make a sign chart. So we're going to make a number line, and, well, again, maybe I should draw this out. I need to animate that better. Our number line, the inputs are x. This is going to be the sign of y prime. There's only one critical value to worry about, and we just need to test intervals. So if you choose any number greater than 0, like 1 or 2 or 3 or 4, negative 4 times a positive number cubed is going to be negative. And so y prime is negative from 0 to infinity, and negative x to the fourth decreases from 0 to infinity. So choose some number less than 0, like negative 1, negative 2. Well, negative 1 cubed is negative 1 times negative 4 is positive. Oh, man, I keep hitting that thing. How do I turn you off? There we go. And then y prime is positive from negative infinity to 0, so negative x to the fourth increases on that interval. All right, let's erase all of that now that we know how to make a sign chart. And our job is to explain what we see. And what I see is, hey, at 0, y prime changes from positive to negative. So we say negative x to the fourth is continuous. At x equals 0, y prime changes from positive to negative. So negative x to the fourth has a local maximum there. Instead of that, you could say, negative x to the fourth has a local maximum at x equals 0. But we do need to refer to a specific place. As in, our evidence happens at x equals 0. In our conclusion, the local maximum, that happens at x equals 0 as well. So we do want to mention that bit twice, even though it feels repetitive. You'll get used to it. All right. Do you know what the graph of x minus 1 to the 2/3 power looks like? So that's just x to the 2/3 power, which has a cusp, shifted to the right 1 unit. And maybe you don't know that graph. So how can we tell if this graph is continuous? Well, let's break it down. Ignore the 2/3 for a moment. Is x minus 1 a continuous graph? Yes, of course. And then don't forget that 2 is like the squaring function. So, x squared or anything squared, that'd be a continuous function. I guess the wild card is that 3. And that 3 represents the cube root. And unlike the square root, the cube root is a continuous function with a domain of all real numbers, so we can confidently say x minus 1 to the 2/3 power is continuous, even if you didn't know the graph. So then, where will this graph have a maximum or a minimum? Critical values. So move that exponent out front, 2/3 of x minus 1 to the negative 1/3 power, and then chain rule times 1. You don't need the times 1, but whenever you have an input other than plain old x, we need to make sure we're using the chain rule. Okay, it's probably best to rearrange. 2 over 3 times the cube root of x minus 1, and then that's pretty obvious that y prime can't be 0, because, when we would set this thing to 0, the first thing we would do is multiply to get rid of the denominator. So we'd get 2 equals 0, and, well, we know 2 can't be equal to 0. And then it's also pretty obvious to me, 1 makes this denominator 0, so we can just make that statement. Y prime is undefined for x equals 1. So now we have a sign chart, and pretty easy to fill out. Ooh, I forgot an x. And you don't have to worry. Remember, we're just worried about the sign. And so I can ignore the 2, I can ignore the 3, those are positive. When I choose a number greater than 1, like 2 or 5 or 10, the cube root of 2 minus 1 is going to be positive. The cube root of 5 minus 1 is going to be positive. All of those are going to be positive. Don't worry about the number. Just worry about the sign. Likewise, if we take an input less than 1, like 0 or negative 10, well, the cube root of 0 minus 1 is going to be negative. So y prime is negative overall, because you have that positive 2 divided by 3 divided by a negative. Okay. So what are we going to write? We're going to write, again, x minus 1 to the 2/3 power is continuous, and then we'll look for evidence. At x equals 1, y prime changes from negative to positive. than our conclusion. So x minus 1 to the 2/3 power has a local minimum at x equals 1. Do we need more examples? I guess one more might work. So, kind of like the last one, you're probably not going to know this graph, but you should know x squared minus 3 is a continuous function. That part's a parabola. E to the x is a continuous function, and multiplication does not create continuity problems. So we'll just say f is continuous and move on. As far as derivatives go, you have to use the product rule. First function, x squared minus 3 times the derivative of e to the x, which is e to the x, plus e to the x times the derivative of the first function, and the derivative of x squared minus 3 is 2x. So then we want to factor out the e to the x. Number one, because it makes our life a little bit easier, and then we realize, oh, we do get two factors out of x squared plus 2x minus 3, namely x plus 3 and x minus 1. So you should know the graph of e to the x is never equal to 0. X plus 3 is equal to 0 when x is negative 3, and x minus 1 is equal to 0 when x equals 1. So our sign chart has two critical values, negative 3 and 1. Now, this is also, well, let's delete that for a second. So we'll put in negative 3, we'll put in 1, because this is a great time to show you, maybe not a trick, but a best practice. And that is, if all we care about is finding the sign of f prime, it doesn't matter which of these three we use, but this last one, oh my gosh, that's the easiest. Because e to the x is always positive. And so all we have to decide is x plus 3 positive, is x minus 1 positive, and then we'll know if f prime is positive or negative. So, if you choose a number greater than 1, e to the x, I don't know, e squared is going to be positive. So let's think, we're thinking f prime of 2. E to the second is positive, 2 plus 3 is positive, and 2 minus 1 is positive. So we get a positive times a positive times a positive is positive. Do you see how we're doing that without really doing work? I'm writing this, so hopefully you can follow, but we really shouldn't be writing anything. So most people will choose the input 0 in between negative 3 and 1, but let's use negative 2. It's just as easy. E to the power negative 2 is positive. Negative 2 plus 3 is positive. And negative 2 minus 1 is negative. So we get a negative overall, and f decreases from negative 3 to 1. All right, get the hang of it. So while I'm erasing, we'll keep looking at that factored form of f prime, and if we choose a number less than negative 3, like negative 10, e to the negative 10 is positive. Negative 10 plus 3 is negative. Negative 10 minus 1 is negative. Negative times a positive is positive. So that's how we come up with that sign chart. Okay, get rid of all that junk. And then, how are we going to conclude? Well, f is continuous. At x equals negative 3, f prime changes from positive to negative. So f has a local maximum at x equals negative 3. Cool. And at 1, what do we see? At x equals 1, f prime changes from negative to positive. So f has a local minimum at x equals 1. All right, I hope you're good to go.